The SN2 and SN1 mechanisms both describe ways of doing substitutions, and thus they share a lot of the factors that affect how well they work. I want to do my best to compare these side by side so we can start linking the concepts. And one of the best place to start is the substrate. And what I mean by substrate is the carbon, the quality of the carbon that the leaving group is attached to, whether it be primary, secondary, or tertiary. So let's consider attempting to do an SN2 mechanism in the top left corner. So let's just say I have a sulfur nucleophile. It's coming into attack, forcing the leaving group to leave. Now here, one of the big considerations, as we mentioned in a couple of videos ago, is how sterically hindered this electrophilic position is. Well, this is a primary carbon, so there are only two hydrogens, so there's not much space being taken up. This nucleophile is able to push through, in a way, and cause the leaving group to leave. Well, let's look at the bottom, right below here, and apply the same process. Same nucleophile, same qualities there. It's coming in to do the backside attack, but there's a little bit of a problem because we have these other carbon groups that are standing in the way of the electrophilic site. That's a lot to push through, and this tertiary position is just going to be an incredible obstacle in an SN2 mechanism, so we're not going to see this happen. On the flip side, let's think of an SN1 mechanism, going to the top right-hand corner. Let's say I have ethanol, so a weaker nucleophile. Well, what we expect in an SN1 mechanism is for the leaving group to leave the substrate, leave the house first. Well, when we do that, as we would expect, we're creating a carbocation. Well, here we have a primary carbocation. It only has one carbon neighbor, so we're not getting a lot of stability given through hyperconjugation. And this SN1 mechanism depends on this being formed for the rate. And since it's unstable, we're less likely to see this. So before this methanol can actually even attack, just the stability isn't there for it to happen, so we wouldn't expect this. It's just the stability of the carbocation isn't there. Let's look right below that. Same process, same idea. We're having the leaving group leave first, and I'll go ahead and draw my ethanol as my nucleophile here. But in this case, let's look at what our carbocation looks like. I have a tertiary carbocation. This carbon has 3 neighbors, the most it could have, and it's being stabilized through this electron density being donated by these neighboring carbons. Since it's stable, it's more likely to exist in the solution, so we can actually have the time, or if we want to consider the rate, for this ethanol to come in and accomplish the attack and form the product we'd want. And thus this is a principal characteristic of the stepwise process. Now, why is this such an important thing to take into consideration when it comes to SN2 and SN1 mechanisms? Well, if you can decide by the substrate what is going to work best, then you don't have to worry about many of the other things. Say, for example, at the top I could say, okay, let's say I had my sulfur nucleophile, then I'm going to have a solvent, and we'll get to that in a few videos, and then I have this, I need to consider the leaving group, and there's so much to consider, but if you just take the time to look at the substrate, that's going to give you a great amount of information. Of course, the main source of ambiguity is when we have a secondary carbon as our substrate, because we're getting kind of this middle of the road. But that's why there are other factors to consider, like the electrophile, the nucleophile, the strength of the nucleophile, and even the solvent that we're doing the reaction in. To make this quick, we'll take the ambiguous example that I wrote just in the previous slide and make 2 different pathways for either SN2 mechanism or SN1, and what things we'll want to choose. Let's start with a nucleophile. We know that SN2 is a concerted process, and we know that we want to forcibly remove or force out the leaving group. So we'd want a strong nucleophile. In this case, one that is most likely has a negative charge. Perhaps it could also be highly polarizable, which would help its nucleophilicity farther. As for the SN1 mechanism, we're used to seeing weaker nucleophiles, and perhaps if I do a bit of an analog of what I just wrote with the ethoxide, we could have ethanol. And that's because before we can even do an attack, we need to open up the space. We need to open up a home by creating a carbocation. Point being that we're truly wanting a strong nucleophile to have this concerted process with SN2 as opposed to SN1. Another thing we can go to is leaving group. Now, leaving group here is interesting because we know that leaving group is good for both SN2 and SN1 mechanisms. So in here, I'll just write the leaving group we have right now. For both these, it's fine. Of course, with SN1, that depends on forming the carbocation, we perhaps might prefer a more stable leaving group, even better than bromine, for example. But still, that's a pretty good leaving group. Thus, since both mechanisms do depend on a good leaving group, it's harder to use that as a way to decide between SN2 and SN1. Finally, we actually have the solvent. And the two choices we have are protic solvents and aprotic solvents. SN2 is going to want an aprotic solvent, and one of them you might see is, is this, commonly referred to as THF. And you see that it has no protons. We're not going to see those hydrogen bonds or these intermolecular forces. Because we're lacking those hydrogens connected to electronegative atoms, we're not getting these solvation shells around our negatively charged nucleophile, which allows it to more easily attack its electrophilic site. Because if we were to have, say, a protic solvent, which we'd want for SN1 mechanisms, if we had that with SN2, then these partial positive charges that we'd see here would cause the water molecules to surround this ethanol and thus hinder its nucleophilicity and its ability to attack the substrate. Of course, in both of these solvents, we are getting partial negative charges that help stabilize perhaps the spectator ion, which might be sodium with SN2, but it also can help stabilize if we had our carbocation in this instance, because we had the partial negative charges near that from our solvent, our dissolved water. Partial negative. Now that was a very quick run through, but in the next video we're going to actually apply these concepts to predict products and choose the correct reagents for what we want, whether an SN2 mechanism or an SN1 mechanism.